In our video today, we're going to be focusing on exponents and the different types of exponents that exist, including the exponent rules or the exponent laws that we work with when we're multiplying, dividing, or adding and subtracting things that involve exponents. To start, remember that an exponent is just a shorthand way in mathematics to let us know that we're multiplying the same thing over and over and over and over again. We say that we're multiplying a number of identical factors. So 4 to the exponent 3 would be the same thing as just writing 4 multiplied by itself 3 different times. Just like x to the exponent 3 is just the same as multiplying x to itself 3 different times. One warning though as we work through these different exponent rules is that order of operations or BEDMAS will always apply. So the exponent is always attached directly to the thing that is being multiplied a certain number of times. For instance, 3x cubed is 3 times x times x times x. Only the x is multiplied to itself 3 times because the 3 is only attached to the x. But 3x times 3x times 3x isn't the same. So if we wanted 3x times 3x times 3x, we would in fact write 3x in brackets to the exponent 3. Now this exponent is attached not only to the x, but also the 3. So that entire thing would be multiplied to itself 3 times. Here's our quick review of all of the exponent laws we've learned. Number 1. When multiplying powers with the same base, we know that the rule is to add the exponents. So for instance, if we have 3 squared times 3 to the exponent 4, then that means that we're going to add the exponents together, 2 plus 4, and that will equal 6. So 3 squared plus 3 to the exponent 4 is equal to 3 to the exponent 6. Mathematically how this works is we're going to write out 3 squared, 3 times 3, and 3 to the exponent 4, 3 times 3 times 3 times 3. And really all that is 6 3's being multiplied together, or 3 to the exponent 6. You can see that division works the same way. 6 to the exponent 5 divided by 6 to the exponent 2, well, if we write them out fully, 5 6's multiplying divided by 2 6's multiplying, some of these 6's can just cancel with each other, and we're left with just 6 times 6 times 6, or 3 6's, or 6 cubed left over. All we did here was we subtracted the exponents. So if we have powers with the same base that are dividing, we subtract the exponents. We'll often see some exponents that are attached to other powers. So 5 squared, which is then cubed, well, the rule here is now we multiply the exponents together. This would be the same thing as saying 5 to the exponent 2 times 3, which is just 5 to the exponent 6. If we have an exponent outside of something where there are two things being multiplied in the brackets, so it's attached to both the 5 and the 2, well, this gets distributed through. So as long as everything is multiplying in the bracket, that's important, everything is multiplying in the bracket, that exponent goes to all those things. So this is the same thing as saying 5 cubed multiplied by 2 cubed. Now these two things have different bases. One has base 5, another has base 2. So there's no exponent law that we can do with them. So we would have to solve these separately. 5 cubed is 125, 2 cubed is equal to 8, and 8 times 125 is 1000. Another way to look at this is to follow some BEDMAS rules. We know in BEDMAS we like to solve the things that are inside the brackets first. So 5 times 2 is 10, so this would also equal just 10 to the exponent 3. Well, 10 cubed is 10 times 10 times 10, which is also equal to 1000. You'll see both of these will get us to the same result. A third rule to keep in mind is the power of a quotient rule. What happens if inside the brackets we're dividing? Again, we can distribute this exponent to both of the things that are inside the bracket. So this would be 2 cubed divided by 5 cubed. And then again, we can simplify this. But there's no exponent rule we can do here because the bases are different. 2 and 5 are not the same base. So we can't do anything with the exponents. So we'll have to just solve each power individually. This is 8 over 125. This rule of putting the exponent into everything in the bracket only works if everything in the bracket is multiplying or dividing. If you have addition or subtraction, you cannot use this rule. Here are some quick examples. M cubed times m to the exponent 4 times n to the exponent 2. We have all the powers which have the same base, and they're all multiplying, so let's add the exponents. 3 plus 4 plus 2 is 9, so this just equals m to the exponent 9. Now we have a monomial, 4x cubed, that's being multiplied to another monomial, 6 times x to the exponent negative 2. That's something new we haven't seen before, a negative exponent. We'll get to those later. But let's just follow the exponent rules. When we have coefficients and variables, we know that we need to multiply the coefficients together first, and then we'll multiply the variables together. The exponent 3 is only attached to the x. It's not attached to the 4. Otherwise, this entire 4x would be in brackets. With the same logic, this negative 2 exponent is only attached to the x. It's not attached to the 6. So let's multiply the coefficients together. 4 times 6, that's 24. And then we'll multiply the variables. They have the same base, so the rule is we can add the exponents because we're multiplying. So 3 plus negative 2, well, that's just 3 minus 2, so that will just leave us with x to the exponent 1, or simply x. So that's just 24x. When we see an example that involves a lot of things multiplying and dividing, what our first step might be to do is to reduce or cancel. We can reduce and cancel here because everything in this question is multiplying or dividing. You're going to see there's no addition or subtraction signs in this entire question. If that's true, then anything in the numerator can reduce or cancel with anything in the denominator. Let's start with the coefficients. We have a negative 6, we have a 3, and we have a 9. Anything in the numerator can reduce with anything in the denominator as long as we're multiplying and dividing. So, for example, this 3 and this 9, we can divide 3 out of both, and this would reduce to 1 and 3. By the same logic, this 3 can now reduce with this negative 6. Both of them we can divide out 3 again, so we'd be left with 1 here and negative 2 here. Looking at the variables, looks like we have an a to the exponent negative 3, an a to the exponent 5, and just an a. Variables can also reduce with each other. So if I have a to the exponent 5, that's like saying I have a multiplied 5 times on top, and a multiplied once below. One of these a's can cancel with one of the a's that was up here. So this would actually turn out to be a to the exponent 4. And same thing with the b's, but let's look at this 1b here and this 1b here. Those can direct cancel. So after all this canceling, what do we have left over? Well, for coefficients, we have negative 2 times 1, and then divide by 1. That just leaves us with negative 2. A to the exponent negative 3 multiplied to a to the exponent 4, add the exponents. Negative 3 plus 4 is 1, so that's just a. And the b's here canceled, we're just left with b to the exponent 4. And our final answer is negative 2a b to the exponent 4. Sometimes we'll see a question like this and our first instinct is to just multiply everything together to start. And we can do that. Let's see what would happen. Negative 6 times 3, multiplying the coefficients together, is negative 18. A cubed times a to the exponent 5, adding the exponents, we end up with a squared. And b times b to the exponent 4, again, adding the exponents, we end up with b to the exponent 5. On the denominator, we still have 9ab. Now we'll do our reducing. Negative 18 divided by 9 is negative 2. A squared divided by a leaves us just with 1a. and b to the exponent of 5 divided by b is b to the exponent of 4. This is exactly what we had before. Either of these methods work out, and it's up to you to decide what method works best for you when you need to simplify a question like this. A new element that you're going to see is something called the zero exponent. So for example, what if we see something, or what if we want to evaluate a power like 3 to the exponent 0? We're going to take a look at how you would even come to something that is 3 to the exponent 0 by looking at a question like this. Let's say we had 3 to the exponent 4. 3 to the exponent 4 is the same thing as just multiplying 3 to itself 4 times. 3 times 3 times 3 times 3. Well, what if I took 3 to the exponent 4 and I divided it by 3 to the exponent 4? Well, that would mean that I would take 3 times 3 times 3 times 3 and divide it by itself, or let's just write this out here. So if I divide both sides by 3 to the exponent 4, we would divide it by the same thing. And hopefully, logically, we can see that each of these 3's would end up reducing or canceling with each other. And when everything reduces in a numerator and everything reduces in a denominator, we're just left with 1. We're not left with nothing, we're left with 1. So to simplify, this would just be 1 over 1, or this just equals 1. Well, if we use exponent rules, 3 to the exponent 4 divided by 3 to the exponent 4, we're dividing powers of the same base, so we subtract the exponents. 4 subtract 4 is 0. Well, now we can see that this is the same logically as this, so 3 to the exponent 0 is equal to 1, which is an interesting thought, because you would never have initially thought that. In fact, anything to the exponent 0 will equal 1. This is true for variables as well. If you have x to the exponent 0, that will also equal 1. We can logically get to the same result by just taking, let's say, x squared divided by x squared. Again, the exponent rules would say that we'd subtract, and we'd end up with x to the exponent 0. We also know logically that any number or anything divided by itself is equal to 1. So that's why this logic works. The only time this logic doesn't work is if the thing that we are dividing by itself is the number 0. 0 divided by 0 is actually undefined. Anytime we divide anything by 0, even 0, we end up with undefined. It's not mathematically possible. So this rule works for any number except if the number is 0. Remember that negative exponent we saw? Yeah, those exist too. And here's logically how they work. Let's take, for example, 2 to the exponent 4 and divide it by 2 to the exponent 7. Using our exponent laws, we would subtract the exponents here, and this would end up with 2 to the exponent negative 3. So how does this get interpreted? Well, if we wrote this out, 2 to the exponent 4 divided by 2 to the exponent 7, we're going to write out all of these things. So this is going to equal 2 times itself 4 times. And then it's also going to be 2 times itself 7 times. That's a lot of 2's I need to write here. 5, 6, and 7. Well, let's reduce or cancel here. Everything's multiplying and dividing, so we can reduce or cancel. In fact, 4 of these 2's are going to reduce with 4 of these 2's. And what we're left with, of course, when everything gets canceled, we're left with 1. So we're left with 1 over 2 times 2 times 2, or that's the same thing as just saying 1 over 2 cubed. So we have this 2 to the exponent negative 3, which is also the same thing as saying 1 over 2 to the exponent positive 3. And mathematically, that's what a negative exponent is. It's in fact 1 divided by the number or the base to the positive version of that exponent. So another way to think of this is if I had 5 to the exponent negative 2, I can rewrite this as 1 over 5 to the exponent positive 2. By putting it as a reciprocal, 1 over, it turns the exponent positive on the same base. Here's the official way to write out that rule. It works for variables as well. So any number to a negative exponent will just equal 1 over that same base to the positive exponent. And of course, we have this rule where that number can't be 0, for simple reasons that we can't divide by 0. So quickly looking at some other examples. 3 to the exponent negative 3. With our rule, we know that we can change this into 1 over 3 to the exponent positive 3. And now we can evaluate. So 3 to the exponent 3 is 27. So this is just equal to 1 over 27. What happens if the negative exponent is already in the denominator? Well, let's logically piece together what we know about negative exponents. It means that we're going to take the reciprocal of this and make it a positive exponent. So we can write this as 1 over 5 to the exponent positive 2. Well, we are now dividing by a fraction. So we can logically say that when we're dividing by fractions, it's the same thing as flipping and multiplying, or multiplying by the reciprocal of the fraction. So this would equal 1 multiplied by the reciprocal, 5 squared over 1. And 1 times anything is just the anything, and 5 squared over 1 is 5 squared. Let's take a look at the logic that happened here. We started with this fraction here and ended up here. Notice how the negative exponent, when it was in the denominator, ended up being the same base with a positive exponent in a numerator, or without a denominator at all. So if it started with a negative exponent in a numerator, it will end up with a positive exponent in a denominator. If it has a negative exponent in a denominator, it will end up with a positive exponent in a numerator, and so on and so forth. Here's an example where we have a fraction to a negative exponent. We have already discussed how in a fraction with an exponent, we can distribute this exponent to both of the things inside the fraction. But we're going to try something a little bit different. Remember, by rule, if we have a negative exponent, we can say that's the same thing as saying 1 over that same base but to a positive exponent. So 1 over 3 to the exponent 4 to the exponent 2. Well, 1 over 3 over 4 to the exponent 2, well, we can distribute that exponent 2. So this would be the same thing as saying 1 over 9 over 16, because 3 squared is 9 and 4 squared is 16. And we're dividing by a fraction, so this will force us to flip and multiply, or multiply the reciprocal. 1 times the reciprocal of this is 16 over 9. Well, 16 over 9 is the same thing as saying 4 squared over 3 squared, which is the same thing as saying 4 over 3 all squared. We'll compare this to our original question. 3 over 4 to the exponent negative 2 turns out it equals 4 over 3 to the exponent positive 2. And this logic always works as well. If you have any fraction, let's say x over y to a negative exponent, it will always equal that same fraction but the reciprocal to the positive version of that exponent. So x over y to the exponent negative n would be the same thing as y over x to the exponent positive n. By taking the reciprocal, it turns the exponent positive. There are some common mistakes that we see here. Sometimes we think that by flipping the fraction, it also turns the fraction positive or negative. So if there was a negative inside the fraction, for example, if we had negative 2 over 7 all to the exponent negative 3, a common mistake is when we take the reciprocal, we also change this fraction to be positive, but that's not true. It's still going to be negative 7 over 2. Remember, the negative we normally float to the top, and this would now be to the exponent positive 3. All we did was take the reciprocal of the fraction, and it turned the exponent positive. Here's our final example, and it's a doozy. 2 to the exponent negative 4 plus 2 to the exponent negative 6, all divided by 2 to the exponent negative 3. We want to use our exponent rules and our logic of negative exponents to try to solve this. But there's one big roadblock in here that is really going to stop everything that we really want to do. And that's this big plus sign right here. This plus sign is a huge stop sign. We need to stop thinking exponent rules, because as soon as we have addition or subtraction, the exponent rules get thrown out the window. They only work when we are multiplying or dividing powers with the same base. As soon as we add, we can't use the exponent rules. So how on earth do we solve this without using exponent rules? We need to actually individually look at each of these powers and solve them or evaluate them individually. So 2 to the exponent negative 4 we know is the same as saying 1 over 2 to the exponent positive 4. And 2 to the exponent negative 6 is the same thing as saying 1 over 2 to the exponent positive 6. And 2 to the exponent negative 3 is the same thing as saying 1 over 2 to the exponent positive 3. Again, no exponent rules can happen. We have an addition sign. So let's look at what these fractions are when we evaluate. 2 to the exponent 4 is equal to 16, so we have 1/16. We're going to add on 1 over 2 to the exponent 6, which is 64, and then we'll divide by 1 over 2 cubed, which is 1/8. To add exponents, we're going to need a common denominator. 16 does go into 64 4 times, so this will be 4/64 plus 1/64, and then we'll divide by 1/8. This leaves us with 5/64 all over 1/8. And we have a fraction that's dividing by a fraction. Well, we've seen before that when we have fraction dividing by fraction, we can flip and multiply, or take the reciprocal and multiply. So 5/64 will then multiply with 8 over 1. And because we have two fractions that are multiplying, everything's multiplying and dividing, we can reduce. So 8 and 64 actually both can be divided by 8. And we're left now with 5 times 1 over 8 times 1, or 5/8. And that's our final answer. All of this stuff here reduced to 5/8. We couldn't use exponent rules, so I can't stress this enough. A lot of times you'll see students or people will try to use the exponent laws with, for instance, these powers of 2. They'll say, -4, we're dividing, so we're going to subtract -3, and that will equal 2 to the exponent -1. And then they'll try to do the same thing and reduce with these two. That cannot happen with this addition sign. Now, one thing that could happen if you wanted to, although I wouldn't really suggest it, is remembering that when we are adding in a numerator, we can have a common denominator and create two different fractions. So this could actually equal 2 to the exponent -4 over 2 to the exponent -3 plus 2 to the exponent -6 over 2 to the exponent -3. If we had a common denominator here, this is what it would look like when we added those fractions together. Now, each of these individual fractions, you can use exponent rules. So the exponent rule would be to subtract -4 minus -3. It's like adding, so that would be 2 to the exponent -1. Same thing here, we're going to treat it like it's adding. So -6 plus 3 is 2 to the exponent -3. And this would equal 1/2 plus 1/8, which is also equal to 5/8. No matter which way you choose, make sure you can be confident with your mathematical abilities. And don't get sucked into just canceling or reducing things when you think you see it. Those addition and subtraction signs will stop you from using a lot of your exponent rules.